So hello, welcome to our lecture 9 of group theory. In this lecture, we will again learn about some more theorems and lectures on group theory. This is our lecture 9. So the first theorem that we will learn is given like this: let G under the binary operation, the group G, the semi group under the not binary composition, and for any two elements AB belongs to G such that AB belongs to G. In each of the equation, A compose X equals to B and Y compose A equals to B has a solution in G. Then prove that G under the set G under the operation binary operation not forms a group. So basically there are two parts are two things are given. G naught is G under the binary operation is a semi group, and the properties of quasi group that A compose X is equals to B and Y compose A is equals to B for any two elements AB belongs to a set has a solution. So first, from the statement we have, since G under the operation binary operation is a semi group, G is closed corresponding to the binary operation, and since it's a semi group, it is also associative. Let E be an element of G satisfying the property A compose X is equals to A, and E dash is a element such that this equation is satisfied Y compose A equals to A. So if we put E in the place of X and E dash in the place of Y, we will get these two equations. Now C be an element in G and P be the solution of the equation A compose X equals to C, and Q be the solution of the equation Y compose A equals to E. So simply we will put, since P is the solution of the equation and Q of A compose X equals to C, we will replace this X by P and get A compose P is equals to C, and replace the Y by Q and get this equation Q compose A equals to C. Now we will take C compose, which can be again written as Q compose by this. Say this equation is given equation A. From A we can write this compose E. Again by associative property we can write this thing like this. We can write Q compose A compose E. This is from associative property. Then the property identity, then by identity property we can write this as Q compose A, and we know Q compose A is again equals to C by this equation A. Since E is arbitrary, C is arbitrary, and A compose E is A for all E belongs to G, this from C, so from here we can say E dash E compose C equals to E compose A compose P, because this we can write this from this part, because E compose P is equals to C. Say this is equation B, and we are taking this as equation 1. We will use it later. Where C is we have till now we have get C is arbitrary, and A compose E is A for all A in G. Because why? Because we have taken an arbitrary element C from the group semi group G and composed with the element E and got what in return C. So C is arbitrary, so we can write it like this now. A compose E is A for all A belongs to G. Similarly we are doing this for, again we're taking an arbitrary element C and composing it with E dash, and in return what we are getting by same procedure we're again getting C. So we can say for any arbitrary element C, there exists for any arbitrary element C, E dash compose A is equals to A for all A belongs to G, since C is arbitrary. Then that's why we can say E dash compose A is equals to A for A belongs to G. So now by equation 1 what we can write? E dash compose E is equals to E dash by this equation 1, since A can be written as E here, so for replacing A as A by E here we can write this, and similarly by equation 2 we can write E compose E is equals to E. So from this equation and this equation we can clearly write E equals to E dash. So thus there exists an element in G such that E compose A equals to A compose E is equals to A for all A belongs to G. So the identity element exists. Now let A dash be an solution of G of the equation A compose X equals to E, and A double dash be a solution of the equation Y compose A equals to E. Basically we are trying to find the inverse of the element. So what we are getting, A compose from this statement we are getting A compose A dash equals to E, and A double dash compose A is again equals to E. Now this is very similar to the previous proof. By associative property we can write A double dash compose A dash equals to A double dash compose A dash. From associative property this we can write this. Now this will become E, and this will become E dash, and from this equation, and this will become E from this equation. Now for the property identity property, again this will be composed with A dash and A double dash, and from identity property we will get A double dash equals to A dash. So A double dash becomes equals to A. Yes, so we are getting what? For all A belongs to G, there exists an element A dash such that A compose A dash is equals to A dash compose A equals to E. So for every element A belongs to G, there exists a unique inverse. So all the four properties, closure, associative, identity, inverse, all are satisfied. So these semi-groups will become a group. Now move on to the next theorem. Let G0 be a semi-group containing a finite number of elements in both the cancellation